Hi, I'm Mr. V, and today we're talking about Illustrative Mathematics, Unit 2, Congruence, and this is the last lesson from this unit, which is called Congruence for Quadrilaterals. By the end of the lesson, you should be able to say, I can use rigid transformations to prove quadrilaterals are congruent. I can write conjectures about quadrilateral congruence. The first thing in this lesson was tell me something that must be true about a parallelogram always, which could be true, and then which absolutely could not be true. So it could never be true. So something that must be true. Both pair of opposite sides are parallel. That's the definition. We've proved that in a parallelogram, both pair of opposite sides must be congruent. Both pair of opposite angles must be congruent. The diagonals must bisect each other. What could possibly be true? Well, if it's a special case of a parallelogram, say it's a rhombus, you could have all four sides be congruent. That's possible. You could have all four angles be congruent. Could have all four angles and all four sides be congruent. You could have your diagonals be perpendicular. You could have your diagonals be congruent. Different things that could be true, but don't have to be true about a parallelogram. And what definitely cannot be true? Well, we have the three families in the quadrilaterals. We have the trapezium, the trapezoid, and the parallelogram. If it's a member of the trapezoid family, so if only one pair of opposite sides is parallel, it would not be a parallelogram. If only one angle was a right angle, or only two angles were right angles, it would not be a parallelogram. If the diagonals did not bisect each other, or if only one of them bisected the other, or if only one of them was a perpendicular bisector. So you can see the idea here. The idea is, do you recognize the properties of parallelograms or of quadrilaterals based on their diagonals and based on their sides, based on their angles? And today we're going to explore that. So for this activity, some things that we know about a parallelogram. First, we know that the opposite sides are both parallel. That's by definition. So I can mark this on here. We know that we've proved that both pair of opposite sides are parallel. So I'll mark that. Are congruent. These two could be congruent. These two can be congruent. We've also proved that both pair of opposite angles must be congruent. So this angle must be congruent to this one, and this one must be congruent to this one. We didn't say that they have to be supplementary, but if the lines are parallel, these two angles would have to add to 180. They'd have to be supplementary. The one thing we haven't talked about yet is the diagonals, and that is right here and right here. In a parallelogram, the diagonals bisect each other. So this side would be the same as this one, and this one here would be the same as this one. They bisect each other. In your reference table, there was some stuff about parallelograms. First of all was the definition in 2.7. Definition is that both pair of opposite sides are parallel. We proved in a parallelogram both pair of opposite sides are congruent. Going down to more about parallelograms, we proved that both pair of opposite angles are congruent. Here we have a rectangle, a definition, a rhombus, a definition. We also proved that in a parallelogram, if one of the angles is a right angle, then it is a rectangle. So those are some things that we proved about it. This is my list that I made, and I did it without a textbook. I came up with opposite sides are parallel by definition. Opposite angles are congruent. Opposite sides are congruent. Diagonals bisect each other. Those are things that we've proved. What I didn't say was that same side angles are supplementary. That means they have to add to 180 degrees because the transversal is crossing parallel lines. And what I didn't say is this last one. If you had one pair of opposite sides is both congruent and parallel, that's sufficient information to prove that the two are a parallelogram. So, okay, fine. Floppy quadrilaterals. So Jada has learned some theorems about triangles, side, 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 angle, side, angle, and the side, side angle sometimes. She wonders if there's any theorems like this about quadrilaterals. And so here's the first question for you to explore. If two parallelograms have all four pairs of corresponding sides congruent, do the parallelograms have to be congruent? Answer the question yes or no. And based on your answer, you're going to get a different prompt to see what you're supposed to do next. Also, here's a short video that I prepared that should help you understand this, and we will come back to this in just a moment to talk about whether it's true or not. Here's one. A parallelogram ABCD and EFGH. Segment AB is congruent to segment EF. BC is congruent to FG, and ABC is congruent to EFG. Those are the side angle side if it was a triangle, but it's not. Are these congruent? And also, I've given you a short video to watch if you wanted to watch it. The activity synthesis. Okay. I need to talk to you just for a moment about this business. If we had two sides at an angle, two sides at an angle, this side is congruent to this one, this side would be congruent to this one, and this angle is congruent to this one. So we have ABC, and D is going to be somewhere over here, E, F, G, F, G, and H is going to be over here somewhere. This is a parallelograms trying to prove that they are congruent. One way to do this is to use triangles. Cut this into, decompose it into triangles. We know the side angle side triangle congruence theorem says that these must be congruent. So that means that there's a rigid transformation that moves this triangle onto here, or a sequence. Maybe it's a translation, reflection, translation, rotation, reflection, whatever. Now, if we apply that same transformation to point D, it will land on point H. That's what we need to prove. That's what we need to show. You could also say that if I rotated this around the midpoint here, that this would, point B ends up over here. So this is where point D is. And I can do the same thing here, rotate it around the midpoint. It's got to end up in the same place. So basically what I'm saying is that you could define some rigid transformations that prove things about parallelograms. You could decompose it into triangles and do this. You could take one rigid motion onto another. And then the last couple of questions here. If points A, B, and C, E, F, and G coincide, what happens to points D and H? Said another way, if the three vertices of a parallelogram line up with three vertices of corresponding vertices of another parallelogram, can the fourth not line up? And the answer to that is no. Back to our first question. If you have four sides, side, side, there is no such parallelogram congruence theorem. Here's the counter example. You could have one that's fatter and one that's squishy, but they have the same properties of congruent sides. Not enough to prove that the two parallelograms are congruent. In this last part, you come up with your own. Is there a shortcut that you can think of? And if you're stuck, may I suggest you try one? Try the one pair of opposite sides is both parallel and congruent. Is that little bit of information enough to prove that the two parallelograms are congruent? You can sketch your thing here. We did not do them more today. If you want to, you can. Lesson synthesis. Go back to the reference chart. Which ideas do you remember about this? How to prove the points in triangles are congruent. So how to know that the theorems that we've proved. Continue learning about theorems and congruence throughout this course. The final thing is the side rectangle congruence theorem states, if we know two corresponding sides, pairs of adjacent sides must be congruent in a pair of rectangles, then the rectangles must be congruent. Explain how you would know this is true. And we go back to this situation, only instead we're going to draw it as a rectangle. So we have two sides of one rectangle and two sides of another that are congruent. If it's a rectangle, that means we know that this has to be a right angle. All four angles are right angle. So I'll draw the other two sides over here. By the side angle side triangle congruence theorem, there's a transformation that maps this one onto this one. Since they are congruent, I can apply that same thing to this last point. And that means these two rectangles have to be congruent. All four sides are congruent. I could also say that we know that it's a parallelogram. We've proved that rectangles are parallelograms. We also know that in a parallelogram, opposite sides are congruent. So this would be another way of saying it. If these two are congruent, the opposite sides are congruent. So, and it's a parallelogram, the opposite sides are congruent. By definition, all four angles are right angles. Since all the angles match up and all of the sides match up, these two rectangles are congruent. And folks, that's all I've got for today. Good luck and success.